Okay, so here I just remarked that for general relativity, it is not exactly equivalent between Lagrangian formulation and the canonical formulation. This is not for general relativity. Probably it is the first theory you have ever seen that these two formulations are not completely equivalent, right? And all the theory you have learned before, they are definitely equivalent, and the Hamiltonian formulation is just that they replace the Lagrangian formalism by first order differential equations, and the two formalisms are completely the same for ordinary system. But in general relativity, because general relativity has diffeomorphism invariance as it's a general covariance theory, it has diffeomorphism invariance as a gauge symmetry, so it's very special. So for the Lagrangian formulation and the Hamiltonian formulation, it's not exactly the same. It's roughly the same, but not exactly the same. The difference is just that the gauge transformation is not anymore a Lie group in Hamiltonian formula, but it is a Lie group in Lagrangian formula. Okay, so let's keep going. By the way, so there's a reference about it if you like. So the reference, so you can have a look, some remark about it. So of course there are a lot of papers about it, but there's one good reference by Lee and Watt. I think it's 1990. I think there's only one paper with name Lee and Watt, so you can easily find this paper. And this paper explain in some perspective why it is so in general relativity, and compare with, for example, electromagnetism.
Is the V1 and the low symmetry a constraint?
Yes, that's
okay. I have it.
So yeah, and also the formula the paper uses so-called covariant phase space. It has some geometrical language.
Yeah.
Paper. But the idea in the end is just that because general relativity is special, it's background independent and general covariant, so it's so the Hamiltonian formalism, in which you need 3+1 decomposition, cause some difference with the Lagrangian formula. Okay. All right. So now okay. So in Hamiltonian, so maybe I didn't really clearly explain why the gauge transformation generated by the constraints are gauge transformations. So so of course you can consider the variables, the variation of the variables generated by constraints, right? By generated by the constraints, right? For any variable q, you can consider the variation of the infinitesimal variation of q generated by the constraints, of course. But why they are called gauge transformation? It is easy to see. The reason is that if you consider Hamiltonian, so now the Hamiltonian, it is in Hamiltonian formalism, Hamiltonian is of course the most important generating function to generate all the dynamics. Okay, and then you can easily see that the Hamiltonian for general relativity, the gauge transformation for the Hamiltonian, it is invariant. Let's see, it's invariant under these transformation generated by constraints equals to 0, and this is delta vector n equals to equals to 0. It is weakly equals to 0. Let's say, because we have to see. So all the physics is on the constraint surface. Okay. The reason is just because H it's very easy. So H is a linear combination of constraints. So H is the linear combination of the constraints. So yeah, and the constraints are first class. The Poisson bracket between constraints give you still constraints, and give you constraint vanishes on constraint surface. So that's why this formula equals to 0. And this is also, you can see this Poisson bracket is just to give you, this is also equals to, this is also gives a C dot of n, right? Because this is a Hamiltonian Poisson bracket with the function C, right? And this give you C dot vector n. So these give you just the time evolution. So this is just the Hamilton equation for the constraint function, right? And this constraint function, yeah, and equals time derivative equals to 0. It's exactly what I mentioned before, that those constraints are consistent, right? So are dynamically consistent. So the time, so once you impose the constraint on the initial surface, and the time evolution cannot break the constraint because of this equation. And ultimately, it's because all those constraints are first class. All right. So now let's come back to the phase space. Let's look at the structure of phase space. So the phase space at the beginning, we have Qij and Pij. So this is of course infinite dimensional, but for illustration, so we build a coordinate in Qij and Pij. And then for in this phase space, we have a constraint surface, right? And this constraint surface is given by C equals to Ci equals to 0 on the constraint surface. Well, maybe I curly. So curly equal, it means that only valid on the constraint surface. Okay, and this constraint surface, so on the constraint surface, you can generate gauge orbit. So you have still have on the constraint surface, and all the variable are P, and of course still P and Q, but you can generate gauge transformation, because we know gauge transformation cannot change physics, and gauge transformation leaves the Hamiltonian invariant. Yeah, so when gauge transformation leaves Hamiltonian invariant, then of course it leaves the equation of motion. So it implies that Hamiltonian is gauge invariant, then the equation of motion is gauge invariant. I forgot to say upstairs. So equation of motion is gauge invariant. So that's the reason why we call it gauge transformation. So gauge transformation is some infinite dimensional transformations which leaves the equation of motion invariant, right? That's what we call gauge transformation. Okay, so now so when we consider those gauge transformations, the gauge transformation give you orbit, right? So it turns out that for the first class constraint, the gauge orbit are just along the constraint surface. So so these are the gauge orbits generated by the n q n p ij and delta n q. So these are the gauge orbits generated by them, and they are all lying on the constraint surface. Lying on constraint surface. Constraint surface. The reason is that, well, the reason is just because of the first class constraint. because suppose you do a gauge transformation of the constraint generated by another constraint, CA, CB, is just FA, BC, BC, CC. Okay, and again, it's weakly equals to 0. So it means that the gauge transformation generated by the first class constraint cannot change, leave the constraint surface invariant. Yeah. So because the first class constraint generate gauge transformation, and this gauge transformation act on another constraint, still weakly equals to 0. So it means that the gauge transformation leaves the constraint surface invariant. It means that gauge transformation leaves constraint. Let's call this constraint surface S. Leaves S invariant. Okay, so because the gauge transformation leaves the constraint surface invariant, then the gauge orbit must be lying on the constraint surface. Okay, so now once we have the gauge orbits, because along the gauge orbit, the fields along the gauge orbit are physically equivalent, because this is just the gauge transformation. It leaves the equation of motion invariant. Yeah, and so all the points along the gauge orbit are physically equivalent. Okay, so now we can consider to make a quotient of this constraint surface by letting this one gauge orbit to be just a point. So let's make a quotient, the constraint surface modulo gauge orbit. Okay, and then it means that every gauge orbit now become a point. Yeah, so here these also become a point. So which means after the quotient, you actually get another manifold. Another manifold. So this is this manifold is a quotient space. Quotient space, or the space of gauge orbit. Space of gauge orbit. And or space of physical degree of freedom. Degree of freedom. Okay, because all the gauge orbits, the degree of freedoms along the gauge orbit are physically equivalent. So which means once we do the quotient, every point on the quotient space is the physical degree of freedom, the real degree of freedom in physics. So these also it is also called there are many names for this space. And this is also called the reduced phase space. So this name is most important one, reduced phase space. Phase space. Yeah. So P reduce. So this is so in every gauge theory. So you also the physical degree of freedom forms the reduced phase space. Yeah, the reduced phase space are the most important physical description for the final physical description of the theory with no gauge redundancy. Because you see the gauge transformation along the gauge orbit, every point along the gauge orbit are physically equivalent. It means that in gauge theory, the description is redundant. This gauge symmetry is not exactly a symmetry, but actually a redundancy. So, and in the reduced phase space, it's a place where you get rid of this redundancy.
Dr. Han,
yeah.
I want to clarify some conceptions. So the gauge transformation can be built as some meta field on the phase space, right?
Sorry, say again. Some
I mean, the gauge transformations can be viewed as some vector fields on the phase space.
Some
Vector fields.
vector fields. The gauge transformation, yes, and the gauge transformation are vector fields. Are generated by vector fields on the phase space. Yes.
And the gauge object is the integral curve of that vector fields.
That's right.
Right?
That's right.
Okay.
No, I mean, so in the language symplectic geometry. So here I don't really want to go into those mathematics about symplectic geometry. But I can mention those names, those terminologies. So here those infinitesimal gauge transformation, they are called Hamiltonian vector fields. Yeah, they are called Hamiltonian vector fields because this is like infinitesimal change of the functions, right? So this is like a vector field act on the function. And then of course the gauge transformation, this is generated by infinitesimal gauge transformations, and this is it's like the integration curve or the diffeomorphisms on the phase space. But this is not a diffeomorphism in space-time, but this is the diffeomorphisms on the phase space generated by those vector fields. Yeah. So this diffeomorphism usually is called Hamiltonian flow. Yeah, it's a flow generated by the vector fields, and these vector fields are called Hamiltonian vector fields. They are called Hamiltonian vector field of constraints, because any function on phase space can generate Hamiltonian flows by using Poisson bracket. Yes, so this is called, so then the constraints generate Hamiltonian flows of the constraints, and those Hamiltonian flows are the gauge transformations. Yeah.
Okay.
Yeah, and those orbits, what I'm drawing is just the Hamiltonian flow.
Okay.
And then you make the quotient of the orbits, you get the reduced phase space. So here I just all the time want to use the language of field theory, do not involve those geometrical language of the phase space, because otherwise I have to spend another lecture on the symplectic geometry.
Okay. Thank you.
So yeah, if you are not familiar with if you are not familiar with those terminologies, and just forget about them. All right. So here let's look, when we look at this reduced phase space, suppose we consider functions on reduced phase space. Functions on reduced phase space. They are so functions on reduced phase space, which means the functions of gauge orbits, and it means that those functions are constant along gauge orbits. So constant. So for those functions, they are constant along gauge orbits. Gauge orbit, and they are constant along gauge orbit. It means that they are gauge invariant. So it means that they are gauge invariant observables. Okay, they are usually gauge invariant. They are indeed gauge invariant observables. Okay. All right. So now you see we have formally defined the reduced phase space, and we wonder, okay, so why we do so much complicated stuff before that? So why didn't we just come into the reduced phase space from the first place and just define Hamiltonian theory on the reduced phase space, and without even mention about metric? Yeah, because metric is clearly not a very good variable in the sense that it has gauge redundancy. Yeah, so why didn't we define general relativity in the reduced phase space? Yeah, and then talk all the time with gauge invariant quantities. Yes, the reason is that it will be complicated. Yeah, it's the description. So when you gain some, when you remove the gauge redundancy, especially for general relativity, so you get a lot of complications. So it's not so easy. It turns out it's not so easy to construct reduced phase space from the first place. It's hard to find gauge invariant observables, and it's much easier to work with variables like metric with certain gauge redundancy. Yeah? And it makes this formula much simpler. And there is I think there's even a theorem or no-go theorem saying that you can construct a gauge invariant quantity, but for generativity, but it definitely involves infinite number of derivatives. So which means you can write down a gauge invariant observable, okay? But this formula for this gauge invariant observable, it involves infinite number of derivatives. So it's hard to write. Otherwise, and of course, there are exceptions for observables which are gauge invariant that doesn't involve infinite number of derivatives, but those are boundary terms. Those are boundary terms. Something we are going to talk about it probably next week. Yeah. So indeed, you can construct gauge invariant observables. They are some standard gauge invariant observables in generativity, but those are boundary terms. And otherwise, it will be super complicated. But in some cases, it will be we will somehow bypass the complication. So in case we couple generativity, couple cube gravity to some matter field, to some certain matter field. So hopefully, the end of this class, I will mention that scheme. Yeah. Okay. So let's come back to this reduced phase space, and so in some so we can make some counting of degree of freedom. So this is the next procedure. So let's first count the original dimension of the phase space. The dimension phase space spanned by P and Q. So this Pij f Qij of x. Clearly, the phase space is infinite dimensional because you have x. So x can go from 1 to x is everywhere. So x is continuous variable. So it means that but we can count the dimension of the phase space at one point of the space. Okay, so we can count. Suppose I fix the point x. Then what is the dimension of the phase space? So you can counting the number of the fields. So these both P and Q, they are symmetric tensors. So which means both of them have 6 components. So I and J goes from 1 to 3. So they are symmetric tensor. So it is both of them has 6 components. So you have 6 plus 6 equals 12, and times infinity because you have infinite number of space-time points. Okay. And this is the original dimension of the phase space. So this is the dimension of the original phase space. Okay, call this phase space P. Okay, so now from that we can derive. We try to derive the dimension of the reduced phase space. Okay, so then firstly we have to reduce dimension to the space to the constraint surface. So let me calculate the constraint surface. Okay, so Ci. So we have 2 kinds of constraints: diffeomorphism and Hamiltonian. Yeah. So at each point you have 4 constraints. So Ci has 3 and the C has 1. So you have 4 times infinity constraints. Okay, so you just subtract them. You get a dimension of the constraint surface equals 8 times infinity. So 12 minus 4 equals to 8. 8 times infinity. Okay, so this is the dimension of the constraint surface, but the constraint surface has gauge orbits. Yeah, has gauge orbits. So you need to make a quotient of the gauge orbits. Yeah, so then you need to count the dimension of the gauge orbit. So gauge transformations, the number of gauge transformations. Okay, again it's 4 times infinity because you have 4 times infinity constraint, and each constraint generates a gauge transformation. So in total, you have the same number of gauge transformation as constraints, 4 times infinity. And then again, so which means you again subtract another 4 times infinity from the dimension of the phase space. So then the result is the reduced phase space. Yeah, 8 minus 4 is 4. Is 4 times infinity. Yeah. Okay, so now we derive that the dimension of the reduced phase space is 4 times infinity. Okay, so you can draw a diagram. So, and the phase reduced phase space is also a phase space. You can find certain position variable and momentum variable, and you have the same number. You must have the same number of position and momentum. Position variable is 2 times infinity number of position, and 2 times infinity number of momentum. Okay, so you have same number of position as momentum. All right. So now, so in the theory, the degree of freedom of the theory, you see, I mean, we have learned classical mechanics. The degree of freedom, so-called degree of freedom of the theory, is the number of position variables, right? So you have free particle, right? You have to consider a free particle, on one dimension. Yeah, your degree of freedom is 1, not 2. Although your phase space is two dimensional. Yeah, your phase space is 2 dimensional, but your degree of freedom is 1, considering a free particle, right? And therefore, the number of degree of freedoms is half of the space, is half of the phase space dimension. So therefore, once we know that the reduced phase space is 4 times infinity, we conclude that the physical degree of freedom of Einstein gravity, Einstein generativity, or Einstein gravity, Einstein gravity is 2 times infinity. So which means 2 per space point. Okay, I hope it is clear. So now you know that for generativity, the degree of freedom is 2. Yeah? And you can also compare with what we learned for linearized gravity. We call linearized gravity. You find indeed the number matches, because for linearized gravity, you find for gravitational waves, you have 2 polarizations. Polarizations of gravitational waves. Okay, so you find indeed these 2 matches these 2. So I mean, for gravitational waves, you exactly find there are 2 polarizations if you fix the momentum k. Yeah, so here is that if you fix a space point x, you get exactly 2 degree of freedom. And these 2 matches. So this is the result of this counting. Okay, so I think we finishes the ADM formulation. Okay. All right. So I think we can. What time is it now? All right. So we can start a little bit about the. Well, okay. So we can start a little bit about the new variable, which is useful for canonical quantization. Let's keep going. Okay, so some preparation for the new variable. So the next step will, for ADM variable, of course, ADM variable is nice and it is very useful, especially for numerical activity. But when we consider quantum gravity, so the next thing we need to do is to find a quantum theory for gravity. So when we quantizing the formalism, and for example, when we replace Q to be operator Q and replace P by operator P, And it turns out ADM formulation is not so nice and in building up Hilbert spaces and also considering quantizing those constraints. And here the scheme is that you have to promote Q to Q hat, just like in quantum mechanics, P to P hat, and then the Hilbert space will be functions will be wave functions of Q. Okay. Functions of Q, and then Q will be a multiplication operator. This is for quantization. Okay, and this is just a little bit about the scheme of the quantization. We have Q, and the Q operator is just a multiplication operator, and P operator will be a derivative operator, just like quantum mechanics. And then, however, here the difference between the quantum mechanics and ordinary quantum field theory is that you have a bunch of constraints. So then you have to promote Cn to C hat n and C vector n to C hat vector n, and to act, and you let those operators Cn hat act on psi equals to 0. You have to solve those so-called constraint equations. So it means that imposing the constraints quantum mechanically. So you have the Hilbert space, which is function of Q, and imposing those operators as constraint equations. Quantum constraint equation. Quantum constraint equations. And especially the first equation, the Hamiltonian constraint, the quantum Hamiltonian constraint. This is so one can write it as a functional derivative equation. So here, because we are doing a field theory, so Q of x, Qij of x is just a multiplication operator, and P hat ij of x equals to I h bar minus I h bar functional derivative of Q. Formally is a functional derivative of Qij. Yeah? So it's a continuous analog of the partial derivative in ordinary quantum mechanics. Yeah. So so then you plug these quantity as an operator inside the expression of C. You can imagine that you will get a complicated expression. So you will get a functional differential equation. Functional differential equation. Yeah. And you can imagine for ordinary differential equation, it's sometimes already hard to solve, but when you have a functional differential equation and which defined on infinite dimensional space, it is super easy to still super hard to solve. Okay, but it has, because it's this is called, this functionally differential equation resulting to Hamiltonian constraints. It has a name. It's called Wheeler-DeWitt equation, because Wheeler and DeWitt first discover this functional differential equation. So this is usually called the Wheeler-DeWitt equation. Okay, but as I said, this is a functional differential equation. This is very difficult to solve. So that's the reason why people don't like to use. People do not like to use ADM formulation to do quantum gravity. So there was very old formalism of quantum gravity in 70s or 60s. People still use ADM formulation, but starting from 80s and 90s, and people try to use other set of variables, so-called Ashka extra new variables to do quantum gravity. And that variable is much more convenient. And this equation can be written down in a more well-defined, in a better way. Okay, so let me talk a little bit toward the ADM formulation, and we are going to talk about toward the Ashitaka new variables, and then we will talk about it in more detail next time. Okay, so the first step toward the Ashitaka variable is the so-called extending the phase space. So we are going to replace the PQ variable to some other variables, which adding some more gauge redundancy. Extend the ADM phase space. Okay. Extend the ADM phase space. Okay, so how to extend it? So because we are going to use the basis, the orthonormal basis, as our canonical variable. So here, so QAB. So before I always use QIJ, the components of the tensor. So here I'm going to just come back with tensor itself with AB as the abstract index. So QAB clearly can be expanded using orthonormal basis, and the components is just the delta IJ. EJA, sorry, EIA, EJB. So here in our previous notation, so this guy we wrote before is EJA. So this is also normal basis in the space. Also normal basis. Well, also normal dual basis. Dual basis on sigma. And this is also called so-called cotetrad, co-triad, sorry. This is called co-triad. And so from this formula, you can see that, and because we are talking about orthonormal basis, so the information of Q is completely stored in the information of EAI, right? And because the coefficient is just constant, we are considering orthonormal basis. The sense of orthonormality is the meaning of the metric, right? And it reflects the meaning of the metric. Yeah. So given the metric, there's a sense of orthonormality, and another metric has another sense of orthonormality. Yeah. So which means the degree of freedom of QAB is completely captured by orthonormal basis. Yeah. So given an orthonormal basis, you can construct Q. So then conversely, suppose you have Q, you can of course get orthonormal basis, but it's not unique. Yeah, it's not unique up to something. So this is something I'm going to talk about. So this is for Q, and for P, because P is related to K, right? P is what's the formula for